All right, now the record is on. So let us revisit the problem. This is the problem that we started off last week. Okay, we already identified that we have 4 degrees of freedom, Q1 and Q2 at the top, and then Q3 and then Q4, at the 2 rollers. Okay, we already created the code metrics. Please note that we have the number of rows equal to the number of degree of freedom of each member. We have 4 rows and we have 5 members, so we have 5 columns. The first column belongs to member number 1, 3012. You can see that. Okay, 3012. That means a degree of freedom involved with a member number 1, and then 0012, 4012, 3040, and then 4000. Okay, we already given the local node like this. This is 1, that is 2. So that means the orientation of the member number 1 is going to be in the quadrant number 1. Then we have 2, 3, 4, and 5. And then we already started off working with member number 1. So this is your member number 1. Remember that? The orientation is like this, okay? Because 1 is here, so two points to that. So this is your 1, that is your points toward the 2. So that is your vector. Okay, so that becomes your angle. So cosine is in quadrant 1, so it's 3/5. Sine is also in quadrant 1, it's 4/5. And we can use the formula. I hope you can recall this one. Okay, let me try to show you again. Where is it? The matrix, okay? Not this one. Okay, that's the one, all right? This is always your formula. Notice this one. But keep in mind that this formula, if you do not plan to do anything drastic, if you want to follow the use of this formula, if you want to follow the classroom, please keep in mind how this formula has been developed. That is based on the this kind of notation, and our angle moves this way, and it's always 1, 2 like that. Okay, some of you may want to do something like strange, but you may have different formula for this one. But this is not okay, because you can have 1, 2 like this as well, but we use the counterclockwise. So if you use 1, 2 like this, your sine cosine will be like that would be your angle. Okay, from time to time I have seen some students using different sine cosine term, because this has been developed based on this 2 pictures. Okay, D1, D2. So if some of you read some other textbooks and where they employ something like D1 and then D2 like this, or you yourself do something like this, and then no, this is the same, right? Let's say this is your D2, this is your D3, this is your D4. You use something different from D1, D2, D3, D4 like you see here. It's not that you're wrong, but you must be mindful that your matrix will not look like this. Okay, so if you want to use your matrix that looks like this, please keep in mind that this has been developed from using this nomenclature. Okay, so now we have this formula. We can use this to construct the global stiffness matrix of each member. Okay, so now we can come back here, and now you can see this is your member number 1. Looks like that. The orientation is like that. So that's why you got cosine and sine like that. The formula is cosine square, sine cosine, sine square. So this first term, that is the cosine square, This is sine, cosine, this is sine, cosine, and then this is sine square. And then when you have the square term for this problem only, it's cosine square is 9/25, sine cosine is 12/25, and then sine square is 16/25. So I'm factoring 25 out. So that's what we have in the end, okay? And we impose the code matrix on it. So 3, 0, 1, 2. Now it says that this component will go on to the third row and the third column of the global stiffness matrix of the entire structure. So this 9 is actually here. Okay, this 1, 2, this 4, actually they are these 4. All right, and then when you look at this one, this is third row, and then 1 and 2. So I can change the color a little bit to demonstrate. Okay, this is third row, column 1, and then column 2. So 9, 12 here. This is this minus 9 and minus 12. I'm sorry. And look at the third column here. To change the color one more time. This is the third column. The first row is minus 9, so it is this one. In the third column again, the second row is minus 12, so it's this one. Okay, so that's how we construct it. And let's put this into the matrix. So if you are ready, I think we shall move on to member number 2. Okay? So member number 2, let me use my note a little bit to facilitate our process. Member number 2 orientation is like this. And we say this is our local node 1, this is our local node 2. So in terms of orientation, you know, use this one. Okay, this is your quadrant. If your 1 is here, right? 1 is here, and it points towards 2, so that becomes your vector. So that means this is your angle. Okay, so now it's in quadrant 2, so that means cosine is positive. I'm sorry. Even I got confused too. Okay, cosine is x, right? Cosine is negative, but sine is still positive. You know, I cannot believe it that in so many years, some students do mess up or did mess up the trigonometry because they would use the same number, but if this is compared to member number 1, you should know that member number 1 orientation is like this, right? And this is the angle. For this member number 2, when this becomes the angle, actually you can use this one. All right, but you have to be mindful of the sign convention. So for this, cosine becomes minus 3/5, and then sine is 4/5. Okay, so I'm trying to be consistent with how I write member number 1. So let me go back a little bit. Okay, I used that and that. Actually, it's black, but that's fine. Okay, so let's move to black now. Okay, and I think EA over L, if we are going to calculate, I think it should look the same. EA over L, that's also E is 2 million. A is 85 square centimeters. And therefore, L, you need to change it into centimeters as well in this case. So that becomes 5 multiplied by 100. Okay, because this is 5 meters long. We have the 3, 4, 5 triangle again. And turns out to be the same as the first one because the member looks similar. It's 34 multiplied by 10 to the power of 4. Okay, and then let me go ahead and try to multiply this out. So the cosine square despite cosine being negative. So cosine square still turns out to be positive, right? So it's 9 over 25. But sine cosine, it is going to be negative this time. So it's minus 12 over 25. And then sine square again is 16 over 25. So I think I can now go ahead and write the matrix for member number 2. Okay. So that is going to be 34 multiplied by 10. It's going to be too small. Let me, I can lasso it, right? Let's see if guys done it before. Oh, how do I paste it now? Okay. Doesn't seem to be that much useful. So no, it doesn't matter. Okay, so let me rewrite it again because you should modify it, right? So K2 here, that's 34 multiplied by 10 to the power of 4. And then we have our matrix. You know, I'm gonna factor 1 over 25 out anyway. So 21 over 25 will be outside. The first term is cosine square as usual. So it's 9. Sine cosine is minus 12. This is minus 12 and then 16. Notice how the orientation changed these two components from plus 12 to minus 12. So be mindful of that. And you should realize by now that you can divide your matrix into 4 small quadrants. The first one and the last one should be similar. So this is 9 minus 12, minus 12, and then 16. And you know, the last 2 quadrants, they will work the opposite way. So if you can remain focused on what you're doing, you should not make any human error. So if this is 9, this become minus 9, minus 16, 12, and 12. And this quadrant is going to be similar to that. So it's minus 9, 12, 12, and minus 16. Okay. Now we just put the code on. And the code for this member, if you can remember, it is 0012. See if I write the code. Okay, I use the red one for the code. Okay, 0012, 0012. You can scratch out 0 with ease. This is not going to get involved, right? So that means only this quadrant will go into the stiffness matrix of the entire structure. Okay, so we can rewrite this as, let me go back again and okay, I use the red one. You can rewrite this by bringing this out. So it's going to be okay, no. So oops, sorry. This is the proper size. 34 multiplied by 10 to the power 4 over 25. And then we would have this coming in directly, right? 9 minus 12, minus 12, 16, and then the rest is 0. You should try to be tidy, you know? Just write down zeros like this. And look like 6, okay? 0, 0. So that will be assembled into the matrix of the entire structure, okay? And then we can do the same for member number 3, okay? 3 should be easy, so, you know, because it is the vertical member, and we have the orientation 1, 2, like that. So in terms of trigonometry, you are having this vector, right? Right there. So that is 0, 1, right? Sine is 1, cosine is 0. Should be straightforward enough. cosine is 0, sine is 1. Because this is basically your y-axis, okay? Still, some years, some students couldn't get this. So if you can't even manage a simple trigonometry, you should think that you shouldn't have fun being an engineer. Okay, so that's that. And EL over L is going to be slightly different because we have different cross-sectional area. So EA over L and length as well. So EA over L becomes 2 million. A is 65. The height is 4 meters. So this is 4 meters. Multiplied by 100. Okay. So this term becomes 32.5 multiplied by 10 to the power 4. So for AK for member 3, it should be straightforward. 32.5 multiplied by 10 to the power 4. Cosine is 0. Sine is 1. So you would expect to have something like this. Okay. And you can break this again into 4 quadrants. Actually, they don't call that quadrant, right? They call it some kind of submatrix, whatever. I don't remember. But again, this should be similar to this. So you have 0, 0, 0, 1. Okay. And then the two remaining submatrices should be opposite. So you have 0, 0, 0, minus 1. 0, 0, 0, minus 1. Okay. And we put our code on. It is for the third member, it is 4, 0, 1, 2, 4, 0, 1, and 2. Again, we can scratch out the 0 like that. Now, don't be confused that about the zeros. Okay, some will come from this matrix, and some will come because there's no involvement, especially in the third row and third column. Again, we can rewrite this as 32.5 multiplied by 10 to the power of 4. There's no denominator because it's only 1 0. Okay, and we can write this. Let's begin with quadrant 1 and 2. So this is the one, right? 1, 2, and 4. So it is 0, 0, 0, 1. This is from this, right? This is from this. And then we don't have anything on the third, so it becomes 0. But on the fourth, first row and second row, it's also 0. So this is from this. This is from that. Okay. We don't have anything on the third row, so it's all 0. And then the fourth row here, you see, incidentally, it's 0 in the first row, second row, and then the fourth row, they're all 0. So it's 0, 0, 0, and 0. So that would be for your third one. Okay, and we can continue to do for the fourth one and then the fifth one. Okay, so let me move on to the next page. Okay, the fourth and the fifth, we are actually using the same orientation, so it should be pretty convenient for us. Okay, that is node 1 and then that is node 2. So again, your orientation this time, oops. Your orientation, if that is 1 at the origin, points towards 2. So basically this is your x-axis. Okay, so it's pretty obvious that your cosine is going to be 1 and sine is going to be 0. Okay, and your EA over L. This is going to be 2 million for your E. Your A is 65 and the length is 3 meters. Multiplied by 100. Okay, so this term is 43.3. Oops. Wednesday, right? Okay. So we are back in business. This is 43.3 multiplied by 10 to the power of 4. Okay. And for member number 4 and 5, it turned out to be the same. K4 and also 5. Now let's write 5 later. Okay. So for 4, we have 43. Oops. Should erase this as well. Very untidy. Okay. It is 43.3 multiplied by 10,000, and this time cosine is 1, so cosine square is 1, the rest is 0. And again, you can divide this into 4 submatrices. It's 1, 0, 0, 0. And okay, the two remaining submatrices should be the opposite. So it's -1, 0, 0, 0, -1, 0, 0, 0. Okay. Now the code for member number 4 is 3040. 3040. So that means you only have this, and this. Okay, so I can just write K4 now. I did not scratch it out because I plan to use it for number 5 as well, you know? So K4, we can rearrange it to be, okay, you have to be a little bit careful because for quadrant number 1 here, because it's the first row and second row, and this is the, yeah, part of the first row and second row is no involvement, and there's no column number 1, number 2, so here is 0, 0, 0, 0, right? So 3 by 3, that's 1. 3 row 4, that's -1. Row 4, column 3, that's -1, and then that's 1. You see how it remains symmetric, right? So that's 4, and then let me erase this and impose code for 5. Okay, now it is the last member number 5, and the code for member number 5 is 4000, 4000. So K5 just basically with this alone. So the rest will be 0. You don't have to do this, but I think it is very convenient if you divide your matrix into the 4 submatrix to see what's going on. Okay, so the only element that comes in will be this one. See, bad handwriting may lead you to believe that this is 6 rather than 0, and then you may mess it up. Notice that we are almost there. And I want you to notice that this is symmetric. This is symmetric. This is symmetric. This is symmetric. And that is also symmetric. So in the end, that means the global stiffness matrix for the entire structure, after you add these 5 up together, should be symmetric. Okay, so I think I'm gonna write this for you again. See, I have enough here, so you know, in the end, this is the step assembly. Assemble. I use the noun. Okay, you say this is to assemble it. Actually, I use this as my step number 4, so it may be useful to try to go back and identify what we have done in each step. Okay. Step number 1 is here. Okay. Generally, you can, excuse me. I didn't see it the last time, but I think it may be useful for you. So that's why I'm coming back to see this. This is step number 1. Okay, that's oh, here we go. It's just a tiny bit, so I didn't cut and paste this. Okay, this is your step number 1. It's called numbering, where we, you know, give all the nodes and stuff, you know. And then step number 2 and 3 here, it's just sort of mixed together. It's the element stiffness matrix. I suppose this shall be your step number 2, and then this shall be your step number 3, using the code to change it. Okay, so back to step number 4, to assemble it, we now just write every matrix together. Okay, so I'm gonna do it from number 1 again. Can I try to copy it? No, I'm gonna mess up again, but it shall be interesting, right? So okay, let me try. And what can I do? Copy, okay. And I can paste it here, I hope. Okay, so that's the number 1. And we can now add this with number 2, okay. That is our 2, yes. Oops, okay. Copy. And then paste. Okay, that's number 2, okay. And then we can add the 3rd one. That means I'm going back up here and fetch this one. Copy. Paste. Okay, it's a little bit off. Right, okay, let's put it here. Okay, you know, I forgot this. I did not copy everything, so just make sure that you don't forget. This also has the term 34 multiplied by 10 to the power of 4 over 25 in front of it. Okay, And we, oh, you know what? Because I didn't maintain number 4 and 5, so I think I'm gonna have to rewrite them here. So plus number 4, which is, oh, I forgot this too, you know. This better be in front. Okay. Oh, actually I have, so I can do that again. Copy, paste, kind of small, expand that a little bit. And then plus the last one. Kind of fun, right? Now I know why you prefer to write on iPad. Let's be this kind of thing. Copy and paste it here. Okay, seems like I messed up again, but you should see what I'm trying to do. I can. It's going to be difficult. Not really, because we can still do this, right? Now it's gone. Why? Can I do it again? It wouldn't. Oh, it's gone. That's fine. I can just write it again here. That this is 0, 0, 0, and 1, right? Okay. So that's the last matrix. And don't forget that we should have the term up front. That makes a little bit more work to do before you sum it up. But I think it's 43.3 multiplied by 10 to the power of 4, right? For both of them. Okay. Now you assemble by adding them up, and you should see the nature of it. That oh, actually I didn't forget. You know, I superimpose it on here. I forgot. So anyway, you should see the nature that this is symmetric, that is symmetric, 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 symmetric. So in the end, your K should turn out to be symmetric. Okay. So now it's K for your structure. Now we assemble the K for each member to form the K of the structure. Now, because I've been using this example for quite some time, and I think I have more examples, but I don't know why I use this one. The number of the degree of freedom of this member, incidentally, is 4. So you have the 4 by 4 matrix for the structure, which may lead you to believe that it is 4 by 4 because you have 4 degrees of freedom for each member. This is just a coincidence. Okay. The size of your structure stiffness matrix should be in accordance with the number of degrees of freedom. In this problem, you have 4 degrees of freedom. So that's why the structure stiffness matrix is 4 by 4. Okay. So in the end, okay, I have 10 to the power of 4 up front. Now I add everything up. You can use the metric setup in your calculator if you can. So this turns out to be 24.48. 0 minus 12.24. 0, 0, 76.0 minus 16.32, 0, and you bet this better be the same, right? Minus 12.24, and this should be minus 16. 0.32, yes. The third one will be different. 55.57 minus 43.33. Now you can guess that this better be 0. This better be 0. This better be minus 43.33. And this is 82.67. Notice that it is symmetric. Okay, and this is your main axis. Okay, see how symmetric your matrix is. And now go back to your structure. You can construct your force matrix. Okay, so let me go back to this. All right, see, you can see now that your force is in Q1 direction. You see, as I said before last week, that if you apply the force where you don't have the degree of freedom, it's no use because it's not going to do anything to your structure, right? I can apply as much force as I want on the hinge support. It's not going to do anything to the structure. Okay, so you only have the force that matters when they or it is applied where you have the degree of freedom. And in this case, it's where your Q1 is. So and it is going in the same direction as Q1. So we can write our force matrix as $60, right? That's Q1, 0, 0, and 0. And of course, your displacement matrix is Q1, Q2, Q3, and then Q4. All right. So in comes step number 5 is to solve this. And it becomes a mathematical problem now. And I have never asked students to solve the metrics in the exam in the past like decade, because, you know, after all, we are trying to focus on engineering stuff, and let's say anything that concerns mathematics should be measured by your mathematics class. Okay, so if you have a D, which is equal to Q1, Q2, Q3, and then Q4. This is going to be equal to, you know, from, let's say, in case you forget, we always have F equals KD, right? So if you want D, it is K inverse multiplied by F, right? So if you do that, it's K inverse. You need to find the inverse of your stiffness matrix. And if it is symmetric, you can certainly find your inverse, okay? If it isn't, something is wrong. If the inverse cannot be calculated, you're done, okay? So that's that, multiply with the force matrix. And you should know, if you have a 4x4 matrix, the inverse is also 4x4, and your force matrix is 4x1. So if you multiply the 4x4 matrix with the 4x1 matrix, you get a 4x1 answer, right? So this is 10 to the power of minus 4. This is 3.068, 0.265, 1.235 and then 0.618. That's the answer. Okay, so now if you want to know how much or what is the force that is acting on your member, we're gonna have to reassign these displacements back to the stiffness matrix of each member. Okay, remember we have the code, right? And we have the stiffness matrix for each member. You can go back and see this. But remember, oops, too much. You have to come back to the matrix before you assign the code, because this is truly the stiffness. This one is the stiffness of your member, not this one. This one is for the system. This one is for the member. And you have the code, right? 3012. So you assign the displacement 3012 back and count and multiply with the stiffness matrix. You're gonna get the force. Okay, but before we do that, I think it ends rather nicely here. So let me finish this first, and you know, as our custom, is there any question? You want me to go back to some point? Question, please. So I suppose there's no question. So I'm going to stop the share. Stop the record.